Europe's urban areas are striving to develop into well-connected multimodal and multi-usage nodes for smart and clean mobility. Multiple tendencies affect urban and interurban areas: urban growth, densification, digitalization, increasing pressure from freight movements, and a shift to a service-oriented economy. New technologies and innovative measures are emerging, but they are not always taken up at a scale that is necessary to meet the climate targets and European transport policy objectives. Along this lesson, it will be shown guidelines for cities to establish how the integration of ground mobility and air mobility strategies can be promoted. To better understand how this integration can take place, first it is needed to have an overview on the current context of urban mobility systems, the main trends, and lastly, to design a framework to perform the integration between modes of transport. Key players on the integration of urban planning and transport policies need to be considered, as well as their potential role on the UAM deployment. The lesson starts by presenting an overview about the integration challenges between ground and air mobility. Secondly, the perspective of the cities as UAM users and ground mobility providers is presented, approaching societal impacts, public concerns, and ethical considerations of UAM deployment. Lastly, the lesson ends by highlighting key issues on the integration between ground and air mobility. Cities are grappling with negative impacts associated with transportation, such as congestion and pollution, as the world population increasingly concentrates in urban areas. To address these issues, cities are implementing various strategies like congestion charges, improving and promoting public transport, and encouraging non-motorized transport. Furthermore, technological advancements in urban mobility, such as automated, connected, electrified, and shared ACES mobility, are opening new pathways towards a decarbonized and sustainable urban transport system, including last-mile delivery via autonomous robots and drones. These changes will affect cities' health, socioeconomic conditions, land use, energy efficiency, and use of renewables. Hence, cities must have appropriate policy frameworks, standards, and planning to manage the transition towards sustainable urban mobility. Cities are soon expected to integrate the emergent concept of air mobility in specific niches of markets and transport segments. Air mobility is an aviation industry term for on-demand and/or automated passenger or cargo carrying air transportation services for urban environments. This innovative concept introduces an added mobility layer to a city's existing network, aiming to contribute for a better and more sustainable commuting system. The lack of homogeneous guidelines and different levels of maturity from cities to face this emergent mobility challenge turns the subject of the integration of ground and air mobility crucial for a successful deployment of the latter one. Transport integration is an organizational process through which the planning and delivery of elements of transport system are brought together across modes, sectors, operators, and institutions with the aim of increasing the net environmental and societal benefits. The UAM deployment must be looked under an approach that promotes the integration of different modes of transport, considering three main imperatives: physical interface between modes, operational integration between modes, service integration. An integrative framework for promoting physical interfaces between different modes of transportation should include examining spatial agglomeration concepts, optimizing multimodal networks, considering institutional dimensions and implementation drivers, and combining value creation and capture in infrastructure and spatial development. The integration of physical infrastructures alone is not sufficient to achieve seamless mobility, and operational integration is necessary. The operational integration ensures that the offered network from different modes is compatible and create added value with its integration. The operational integration is strongly related with the service integration layer, which allows a commuter to use the same service system to get different modes of transport within a specific area. Service integration is currently facing a substantial transformation phase building on new technological trends such as the Internet of Things, factories of the future, artificial neural networks, big data analytics, autonomous network systems, or smart city reference architectures. Such tools open a wide market possibility of integration between an increasing number of different modes of transport and mobility options. The concept of smart city is a place where traditional networks and services are made more efficient with the use of digital and telecommunication technologies for the benefit of its inhabitants and business. A smart city goes beyond the use of information and communication technologies, ICT, for better resource use and less emissions, assuring a more interactive and responsive city administration, safer public spaces, and meeting the needs of an aging population. In an era of increasing ICT to support urban functionalities, municipalities are also part of this ecosystem and have the potential to examine, understand, and define their own specific urban data, to work out and implement the necessary processes for data provisioning and data management, to build a powerful data infrastructure to support and automate these processes and to ensure their own municipal data sovereignty. The integration of air mobility in European cities faces emergent challenges, and three key players can provide guidelines and support to address them. The European Initiative, the marketplace of the European Innovation Partnership on Smart Cities and Communities, EIPSCC, City Vitality and Sustainability, Civitas, and ELTIS offer tools, good practices, and communication channels to help cities become models of sustainable urban mobility. EIPSCC has an UAM action that steers its activities on smart mobility initiatives, interfacing or enabling UAM by addressing UAM interfaces with public transport, mobility as a service, ground infrastructure for UAM, and ATM-UTM concepts for UAM integration. The third dimension of air mobility is still not a pertinent topic for most European cities, and therefore it is still not a relevant topic for Civitas and ELTIS, but it could be desirably included in SUMPs. The integration of the vertical transport segment with ground mobility system in urban and peri-urban environments, to the overall extent of implementing the concept of mobility as a service, has not been broadly implemented, which makes it difficult to extrapolate assumptions or conclusions about the few existing examples. There are few areas where those services of UAM are currently operating, and the city's socio-demographic characteristics that contribute for that demand are diverse. Integrating UAM within ground mobility is an emergent trend but still strongly dependent on factors like commuter behavior changes, national deployment strategies, population welfare, and safety issues. The integration of UAM services in the overall urban transport chain must incorporate three main indicators of sustainability: societal impacts of transport activities, public concerns, and public acceptance and ethics. Societal impacts refer to both potential benefits and negative impacts of UAM affecting society. The deployment of drones has potential benefits such as reducing traffic congestion and improving healthcare, delivery, and search and rescue services. However, concerns have arisen regarding job losses, limitations in adverse weather conditions, noise pollution, and aesthetic impact on the environment. The deployment of UAM sustainable systems must consider public concerns and acceptance, including safety and security. Concerns include the consequences of malfunctioning navigation systems, collisions with people, cargo loss, and misuse of data or terrorist acts. Communication between drones and controllers using Wi-Fi networks is also vulnerable to security breaches. To gain public acceptance, trust, and transparency in UAM integration strategy are crucial. UAMs also offer advantages for security purposes, such as providing broadband data rates in emergency and public safety situations, search and rescue, and creating unmanned aerial base stations during natural disasters or extreme events to improve coverage and save lives. They can also be used for surveillance during war situations and to avoid human casualties. Overall, while there are concerns, UAMs have great potential for enhancing security and emergency response capabilities. The social sustainability of UAM faces ethical concerns related to privacy violations and lack of transparency. Drones can fly at significant heights, causing privacy infringements, and can be used for espionage and surveillance. Legal frameworks and real-time privacy impact assessments are needed to address these issues. Personal data should be anonymized or removed to prevent its dissemination without consent. Autonomous transportation, like drones, may generate ethical issues such as social inequalities and less inclusive means of transport. Advanced air mobility involves innovative aviation technologies such as small drones, electric aircraft, and automated air traffic management, and includes personal eVTOL, public transport UAM, and short-haul point-to-point business and intercity travel. UAM can provide passenger services, public safety, medical and rescue services, news gathering, ground traffic assessment, weather monitoring, and package delivery. However, there are multiple challenges to overcome, such as the availability of ground infrastructure, nuisances caused by urban air traffic, and flight approval depending on the certification of pilots, vehicles, and operations. To successfully implement UAM, there is a need for a new air transportation system with advances in air vehicles and their operation, airspace system design and operations management, and community integration and acceptance. The main factors that are expected to influence the implementation of urban air mobility strategies include economic drivers, regulations, technology development, social acceptance, and infrastructure. In what refers to technology development, it is expected that the major contribution to UAM is vertical takeoff and landing, VTOL aircraft, which embraces the door-to-door, D2D paradigm. Other enabling technologies for UAM include short takeoff and landing, STOL aircraft, and personal air transport system PATS aircraft. The main challenges for implementing UAM strategies are developing safe, reliable, and certifiable UAM vehicles and operations, including the safety and reliability of electric power systems and electric power trains. The most accredited candidate technologies for passenger transport in the UAM framework are eVTOL and PATS vehicles, the implementation of UAM vehicle strategies, the integration of infrastructure, electrification, and accessible costs, as well as addressing social acceptance factors. Sustainability and technology integrability are critical aspects to consider in UAM infrastructure development, including the development of new runways on building roofs and the availability of STOL, VTOL, and PATS technologies. The integrability of these systems will have a significant impact on the urban infrastructures. A depth analysis of infrastructures and prices of public transport services is needed to ensure an optimal price and investment that affect acceptability. Improvements in endurance and weather resilience will depend on technological developments relating to vehicles, while integrability will involve regulatory aspects and urban infrastructures. The integration of technology in multimodal transport requires digitization in road and air transport, and the integration of air and road traffic management systems. Urban air mobility UAM solutions can be applied to automated road transport for multimodal vehicles. POP.UP is a modular system for multimodal transportation that utilizes ground and airspace, consisting of a passenger capsule, ground module, and air module. Passengers can switch between modes of transportation, and the modules autonomously return to recharge stations after use. This system aligns with the deployment of UAM, providing both surface and air transportation to reduce city traffic congestion. The integration of urban air mobility, UAM, with cities' networks and systems requires consideration of several key aspects. Firstly, UAM is not yet on the agenda of most cities, and regulation, infrastructure, and public perception need to be addressed. Secondly, UAM will likely find its niche in specific markets, which will influence integration requirements. Thirdly, UAM needs to be integrated into the wider city system with safety, security, public acceptance, regulatory and organizational aspects, operational and service concepts, infrastructure adaptation, and sustainability all needing to be addressed. Overall, a multimodal approach is required for efficient and seamless door-to-door mobility.